Okay, so we talked about the torque speed characteristic and how you can uh, bring changes to that characteristic for the maximum torque to happen at startup conditions. So we came up with this rotor resistance. However, this rotor resistance approach has some trade-offs. You need to increase the rotor resistance, right? So when you increase the rotor resistance, you get the higher starting torque, but it results in lower efficiency because you're increasing the losses of the machine. On the other hand, if you have low rotor resistance, you would have lower starting torque, but you would have better efficiency. So therefore, you need to have a compromise between the two. You have to have a compromise between the two. In wound rotor motors, you can basically add the external resistance at the starting and then remove it for efficient running of the machine. However, the downside is that the wound rotor motor is more costly. It requires higher maintenance. It is more complex to control, and it is harder to fully enclose the motor for hazardous environments because you have to get basically the rotor terminals connected to external resistance, and this might not be very feasible. So what other solutions can we have? The ideal motor behavior would be that higher slips, or at the starting, we would have the higher rotor resistance, which gives us a good starting torque. At lower slips, or when the motor is running close to the full load conditions, we want lower rotor resistance behavior or good efficiency. Now, there is another approach that we can talk about when talking about the start torque. So if you want to have the starting torque and maximize the S-max, you could increase R2, but you could also decrease X2, right? And X2 is the leakage reactance of the rotor at locked rotor conditions, transferred to the stators. So basically, that's the other approach, using the leakage reactance of the rotor. So it turns out that placement of the rotor bars will affect that leakage reactance. If you put the rotor bars of the machine, if you put them near the surface, you would have lower leakage reactance and lower resistance. But if you put those bars deeper in the rotor, it results in higher leakage reactance. So again, look at it here in more detail. Effect of the rotor's leakage reactance on torque. The rotor's leakage reactance is X2 equal to A effective squared times XR0. And start top, or S equal to 1, if X2 is comparatively smaller, and you can see it from the torque equation in here also, if you put S equal to 1 and decrease X2, then you would get a higher torque. So therefore, again, placement of the rotor bars affects this. Therefore, designers have come up with designs that can provide this condition for us at startup conditions. Right designing of the rotor can control this torque speed characteristics without the use of external resistance or without having a wound rotor. This is basically done through different classes of induction motors based on NEMA. So NEMA is the National Electrical Manufacturers Association, which based on their recommendation, we have 4 types of designs in induction motors. The first one is Class A, or the standard design. This is showing a schematics of that. Rotor construction is such that large bars are placed near the surface. In terms of electrical characteristics, we have low rotor resistance, low leakage reactance. So in terms of performance, it has higher efficiency because of low rotor resistance. And it can provide a moderate starting torque, but it has very high starting current. So that's a drawback. The applications are in fans, pumps, blowers, and machine tools. Once this design was very common, but now it's been largely replaced by Class B due to the high inrush current. So inrush current is the current at startup of the machine, which is quite high in this Class A design. So therefore, we have another design, which is Class B. Class B is a deep bar rotor basically design, which has deep bars embedded into the rotor core. In terms of electrical characteristics or normal operation, at lower slips or normal operation, when you are close to the synchronous speed, current penetrates the full bar, therefore it provides the low resistance, low losses. And at high slip or starting, it can create currents that are concentrated near the surface, therefore higher resistance and boosting torque. The performance overall is similar starting torque to Class A, but has lower starting current, and it has excellent efficiency. So this design B overall has been able to remove the drawback of Class A, which had a very high starting current. So it can give us basically higher starting torque while lowering the starting current. The applications would be general purpose loads. Now, the most widely used NEMA design would be Class B. There is another class, Class C, two more classes, Class C, which is called the double cage rotor. You can see that it's as if you have two layers of bars. The outer has higher resistance bar near the surface, and inner, which is providing lower resistance, deep bars. The characteristics are the outer cage dominates at high slip or high resistance or high starting torque. And both cages conduct at low slip, which gives us low resistance and good efficiency. So the performance would be high starting torque, low starting current, and low slip at full load. The applications would be loads requiring strong starting torque, such as compressors, loaded pumps, and conveyors. So this is overall giving you basically higher starting torque compared to Class B. And finally, you have the Class D, which is high resistance rotor. The rotor construction is having small diameter bars near the surface made of high resistance material. Electrical characteristic is high rotor resistance, low leakage reactance, which gives you basically a high torque, starting torque. Both cages conduct at low slip, low resistance, and good efficiency. Performance is very high starting torque, low starting current, but it has an overall high full load slip. So we said that under full load conditions, we don't want the slip to be very high. We want it to be as close as possible to zero. But this design is having a 7 to approximately 17% of full load slip, which results in reduced efficiency. The applications is very high inertia systems like punch presses, flywheels, where gradual acceleration is acceptable. So this is design of Class D. And there are two obsolete design classes, which are classes E and F, or soft start designs, where the rotor construction is deeply buried bars, resulting in very high leakage reactance. And their performance would be very low starting current, but also low starting torque. They're no longer in use due to limited applicability and poor starting performance. So if you want to have like a comparative schematics associated with different designs, these are basically, this is Class A, Class B, C, and D. And here is basically a table that kind of summarizes whatever we talked about, the four common classes of induction motor. Now, let's again look at starting induction motors and the key points associated with that. Induction motors generally start more easily compared to synchronous motors and can often be started directly across the line. So we can directly, in most cases, connect them to the line in order to start. However, due to some circumstances that result in high rush current, that can lead to voltage dips in the power system in the nearby loads, which sometimes can make it unacceptable. So in order to avoid that, so we said most circumstances you can directly connect them to line to start the motor. In some cases, you may affect other loads that are nearby. In order to avoid that, there are basically some solutions. either having a wound rotor motor and started with external resistance added to the rotor second, which also helps with the startup torque. The benefits is that increases the starting torque and reduces the starting current. If you do not have a wound rotor motor, for the squirrel cage motors, the starting current varies depending on the motor rating or the horsepower of the motor and effective rotor resistance at start. Those motors use a code letter, which is not to be confused with the NEMA design class, which is printed on the nameplate to estimate the starting current. So if you do not have the wound rotor motor condition, you have a squirrel cage, you want to get an understanding of what the starting current of the machine is, you need to use basically the code letter in the machine. The code letter defines a range for starting the apparent power in kVA per HP per horsepower. So let's take a look at this. These are the nominal code letters, A, B, C, D, all the way through V. Under locked rotor conditions, locked rotor means when you lock the rotor or at startup conditions, close to startup conditions, right? In order to get an understanding of how you can estimate the starting current, you need to read the motor's nameplate, what nameplate is there, and then what would be the code letter associated with that nameplate. Find the rated horsepower of the machine, find the rated voltage, find that code letter, as I said before. Use the code letter to get the idea of what kVA per horsepower of the machine you have. And then you can find the S of the start by multiplying that rated horsepower of the machine multiplied by the code letter factor that you read from here. And then you can come up with computing the starting current using this equation. Let's do an example. What is the starting current of a 15 horsepower 208 volt code letter F three-phase induction motor? So to do that, let's look at code letter F, which is 5 to 5.6 kVA per horsepower. So we find the maximum in the range, 5.6. Multiply that by the horsepower of the machine. S at the start would be around 84 kVA. And you put that S start divided by square root of 3 times V terminal. V terminal is 208 to get an idea of what the starting current of the machine would be, 233 amps. So you need to make sure that you can tolerate these conditions in the power system. Okay, now let's deal with the speed control in induction motors. So we said that in most circumstances, under full load conditions, the induction motor works close to the synchronous speed. So this is the synchronous speed, depends on Fs, depends on P. So you can right now get an idea of how you can control the speed in an induction motor. If you're able to change the input frequency, you would be able to impact end synchronous, and that impacts basically the full load speed of the machine. Also, if you are able to change the number of poles, which sometimes we can do that by changing the stator winding configuration, we would be able to impact the synchronous speed and so the speed of the motor in general. So that's through changing the rotor's speed using the concept of changing the synchronous speed of the machine. We can also change the line voltage in order to impact the synchronous speed, and we can change the rotor's resistance. The rotor resistance, we talked about that before, right? When you change the rotor resistance, you can change the shape of the torque versus the speed characteristics, and so you can change the speed of, you can have an impact on the speed of the motor. Now let's look at these in more detail. Talking about the input frequency, changing the line's frequency while you are below the base speed of the machine. That can happen using VFDs or variable frequency drivers. If you have a variable frequency drive system, then you can control the frequency of the source. Changing the stator frequency shifts the no-load point on the torque speed curve. Base speed is the motor's synchronous speed at the rated frequency. So if you have the rated frequency, the base speed would be the synchronous speed under that frequency. If you are below the base speed, if you're operating the machine below the base speed, then you should note that the stator's voltage must decrease linearly as you are decreasing the frequency. So suppose that you have a certain speed. You want to basically reduce that speed by lowering the input frequency. Because if you lower the input frequency, you can reduce the synchronous speed, and so you can reduce the speed also. So in order to do that, you need to pay attention to the fact that you should also reduce the voltage source, the voltage value on the source. This approach is called derating. So that's because you are decreasing both the frequency of the source and voltage of the source. Why? Why are we reducing the voltage of the source as we are changing or decreasing the frequency at the same time? That's because we should pay attention to the fact that the flux in the machine is proportional to the voltage over frequency. So if you are decreasing the frequency and you are not decreasing the voltage proportionally, you would be increasing the flux, right? And increasing the flux might have the danger of going into saturation or causing excessive magnetization current. Because we know that E is proportional to phi omega. If you're keeping E at the same value and reducing omega, it means that phi should increase, right? So through both of these basically statements, you can come up with the conclusion that if you are decreasing the frequency, then you should also decrease the voltage proportionally to avoid that excessive magnetization current in the motor. And this is called VF ratio, constant VF ratio constant. So constant VF ratio maintains the constant flux and also produces the same predicted torque that you were expecting from the machine, because torque is proportional to phi times I, okay? So if you're not changing the phi and you're not changing the I to a lot of extent, the tau induced would be at the same expected value. So you can provide the same predicted torque using this approach. And you can avoid the magnetic saturation, as was said before. However, there is basically a drawback. So nothing would be ideal at all conditions. There's always some drawbacks, pros and cons. The power capability decreases linearly with voltage and frequency because you're lowering the voltage. Therefore, you're lowering the power. Voltage drops, power must drop to prevent overheating. So there is an approach that you might basically want to have the same power while decreasing the voltage. This means that you have to increase the current, but that cannot happen either because the increased currents will result in overheating. So therefore, this approach, there's nothing you can do about it. The power would also decrease based on this constant VF ratio constant. All right, now we were under the base speed. What if we want to go and control the speed of the motor above the base speed, which means that we want to increase the frequency? Under these circumstances, stator voltage would need to be held constant. So you would not want to linearly increase the voltage as you are increasing the frequency to maintain the constant VF. That doesn't work if you're going above the base speed. Why? That's because increasing the voltage would hurt the insulation in the machine. So you want to protect the insulation in the machine. That's why you don't want to go over voltage. Because of that, if you're increasing F and keeping V constant, this means that you are reducing the flux, right? And torque capability will decrease because you are decreasing the torque, the flux. When you are decreasing the flux, then you're decreasing the tau. This results in almost constant power and variable torque operation when you are above the base. So overall, basically, these are the conditions for the below base speed as you're changing the frequency or lowering the frequency. when you're increasing the frequency above the base speed, then you should be working based on constant voltage constant. So here, below the base speed, we have constant VF ratio. Above the base speed, we have constant voltage constant. So overall, in practical implementations, the modern solid-state VFDs basically can come up with are widely adopted and can basically provide a good control over the speed in the machine. It is much more, using VFDs is much more versatile than pole changing motors. So even if you are able to change the number of poles in the machine, you have to come up with a changing in or providing some special stator winding conditions, which may not be practical in many circumstances. Also, VFDs can be used with any induction motor, pretty much, because that's how you are inputting your motor, right? So as long as you have those input terminals in the motor available, connect that to the VFD, and you should be able to do a lot of control in the machine for flexible and efficient speed control. Here, the table is a summary of changing line frequency with VFDs. So there are different columns: speed region, voltage, frequency, VF ratio, flux, torque, power, operating mode. So when you are below the base speed, at the base speed, and above the base speed. So this is giving you basically the summary of what we were saying. So when you are below the base speed, the voltage will need to decrease with F. Frequency would be decreasing. VF ratio would be maintained at constant value. Flux would be constant. Torque would be constant and limited by the current. Power would be decreasing with speed. And the operating mode is constant torque, variable power. And you can read the rest at the base speed and above the base speed likewise. So now let's go to changing the line voltage. So we change the frequency using VFDs. How about changing the line voltage? The torque developed by an induction motor is approximately proportional to the square of the applied voltage. So tau induced would be proportional to V squared. Therefore, by reducing the line voltage, the motor will produce less torque, which slows it down if the load torque requirements remain constant. So this method, reducing the voltage, can be used to control the motor speed over a limited range because of that basically torque drawback, particularly for loads where torque decreases with speed, such as fans and blowers. So certain applications can use this approach. Basically, reducing the voltage is not suitable for constant torque loads or large motors due to poor efficiency, increased slip and losses, reduced power factor, and risk of overheating at lower speeds. So typically, speed control by varying the line voltage is used for small motors with variable torque loads, where simple and inexpensive speed control is acceptable. If you do not have the VFDs basically in hand, then this approach can be used for small motors. Also changing the speed or speed control by changing the rotor resistance in the wound rotor motors. Obviously, cannot be used for squirrel cage induction motors. Extra resistances would be inserted into the rotor circuit to reshape the torque speed characteristic. Increasing the rotor resistance would shift the operating point to higher slip or lower speed, would allow the speed control by adjusting resistance to match the load's torque speed curve. And this method is useful for matching motor behavior to varying load requirements, especially when gradual speed control is needed. Major drawbacks is that significant efficiency loss would be because of increased RI squared losses or copper losses. Heat is dissipated in external resistors, not energy efficient for a continuous usage. Typically used for short duration speed control, such as in acceleration, temporary load adjustments, and applications like cranes, hoists, or lifts. Okay, now let's talk more about these VFDs, or solid-state variable frequency drives, which are used for induction motors. Modern VFDs are the preferred method because they can control both the frequency and the voltage. They can accept single-phase or three-phase inputs in different ranges of voltage and frequency. They can produce three-phase outputs in a varying range of frequency and voltage. The type of control that is done in these VFDs is called PWM, or pulse width modulation. So it is based on basically creating the desired waveform out of very fast switching of the solid state switches in order to basically come up with the switching the voltages between 0 and certain values, like what you see here. But this has the advantage that overall it can produce basically the fundamental portion of the voltage that is controllable in both magnitude and angle. So this is called PWM, pulse width modulation approach, which allows independent control of both output voltage and frequency, can maintain basically constant frequency with variable voltage, constant voltage with variable frequency, or it can vary both linearly, constant based on basically constant VF control, constant voltage over frequency. So this figure 746 is demonstrating frequency variation while keeping the RMS voltage constant. So the RMS voltage, the peak value of the voltage would be remaining constant. The frequency is changing. Here we have a higher frequency than here. So this is 60 hertz frequency. Here we have the 30 hertz frequency. In the other figure, 747, we're having the voltage variations while keeping the frequency constant. So both of these waveforms, the fundamental waveforms, have the 60 hertz. In one of them, we have 120 volts. On the other, we have 60 volts RMS value. But in both cases, you can see that all of these have been using the switchings. The switching is always happening between 0 on the positive side and 0 and minus on the negative side. 0 and minus. That's only the switchings, the duration of these pulses that will basically make that fundamental voltage to range in this wide values of, for example, 60 volts all the way up to 120 volts. So that's called the same thing that we call PWM, or pulse width modulation. And now here we have constant VF, which is changing both the frequency and voltage linearly together. So figure 748A is outputting for 60 hertz and 120 volts. Figure 748B is outputting 30 hertz, 60 volts. Figure 748C is outputting 20 hertz and 40 volts. You can see that volt over frequency is, the volt over frequency is 2. Here is 2. Here is 2. So V over F has remained constant. And consider also the peak voltage is remaining the same, as I said, is 0 to or 0 to minus on the minus sign. But you can see that the pulses, the width of the pulses is controlling what we call the V over F constant value. All right. The other features associated with VFDs is that they provide adjustable acceleration and deceleration ramps. So you can increase or decrease the VF ratio, for example, based on an accelerating or decelerating ramps. VFDs don't change motor speed instantly. That's because you don't want to have instant changes. If you go from one value all of a sudden to another value of voltage, for example, it results in some transient conditions that you want to avoid. When we are electronically limiting those acceleration and deceleration ramps for safety concerns, and are independently adjustable for both voltage and frequency also. The motor protection features, VFDs include protection against overloads, steady state overcurrent values, overcurrent spikes, over voltage or under voltage values, and they will shut down the motor if unsafe conditions are detected. So pretty versatile use of VFD drives for control purposes in induction motors. Okay, now let's go to determination of the equivalent circuit parameters. When we talked about transformers, we came up with a few measurements in order to come up with the estimation of the transformer parameters. Here, we also have the same concept. Using 3 major tests, we want to come up with the equivalent circuit parameters of the motor. So this first one is called the, what we want is that we want to estimate R1, X1, R2, X1, X2, RC, XM, all of these parameters associated with the induction motors. This is done through three practical tests, as described in IEEE Standard 112. The no-load test, the setup is based on this. You have basically the motor running freely with only friction and windage loads, basically. Power, voltage, and current would be measured. So power, voltage, and amps are measured when you are under no-load conditions. Slip would be very small, close to zero. Most of the current goes for stator copper losses, and the rotational losses, which is associated with the friction, windage, core. And also magnetizing reactance. The current goes for these purposes. The purpose of this no-load test is to come up with finding RC and XM. It estimates the rotational losses. Since the input current is largely magnetizing, the power factor would be very low. And we would find X1 plus XM. You can find XM if X1 is known, and we will see how we can determine the rest of the parameters, the X1, for example, in here. So this is the no-load test. The other test would be the DC test. The DC test would basically be applied to the stator. We would apply DC voltage to two stator terminals of a Y-connected motor, for example, in here, to find out R1. R1 would be VDC over 2 times IDC of what we measure in here. It is performed under rated current to account for operating temperature. And finally, the third test would be called the locked rotor test. We're locking the rotor, so the slip would be 1. The purpose is to find out R1 plus R2 and X1 plus X2 referred to the stator. So whatever we measure from the rotor would be referred to the stator because we are applying basically the experiment on the stator side. We use the low frequency input. So we do not usually operate this test under nominal frequency. We use it under 25% of the rated frequency to better reflect the rotor's behavior. From the measured basically values, input power, voltage, and amps, we find the power factor, impedance angle, magnitude, and angle of the total impedance, and then solve for R LR and XLR, where RLR is R1 plus R2, XLR is X1 plus X2. And then, since the rotor resistance varies with frequency, especially in design classes B and C, we need to pay attention to that, and also scale reactance to rated frequency. So this is the testing condition in the frequency. This is the rated condition. X-rated would be XLR times this value. All right, so in order to split X1 and X2, it depends on basically, so we said we find X1 plus X2 out of the locked rotor test, but how to split that, it depends on the design. So if you have a design A, half of this value would go for X1, the other half for X2, and so on and so forth for the rest of the designs. And this is a summary table, but really, I mean, what can determine it better would be an example. So in this example, you have the DC no-load and locked rotor tests, and you can see through this procedure that the different values have been found for the motor, and the motor is based on design A. So once you find X1 plus X2, half of it would go for X1, the other half would go for X2. So I want you to take a look at this example. This is also one of your homework problems that you would need to do in MATLAB. And last but not least, let's take a look at induction motor ratings. So output power, voltage rating, current rating, power factor, speed, nominal efficiency, NEMA design, and starting code. Starting code was used for estimating the in-rush current range of your motor. So voltage rating considerations, the voltage limits are governed by magnetizing current. Excessive magnetizing current can cause heating and losses, so therefore you don't want to go over voltage. Derating for lower frequency operation, keep that in mind. A 60 hertz motor can be used in a 50 hertz system, but you need to reduce the voltage proportionally to maintain constant V over F. Current and power limits. Current rating is based on the maximum allowable heating in the stator winding. Power rating in general would be a function of voltage, current, power factor, and efficiency. A few words on induction generators. So an induction motor becomes a generator when you are operating the machine above the synchronous speed. So if your prime mover is working above the synchronous speed, you would be able to generate power. There are some limitations for induction generators. There is no separate field winding like the field winding that we had for synchronous generators. Therefore, they cannot generate reactive power. In fact, induction generators would require some reactive power to be able to operate and give active power. Therefore, we need external sources. The terminal voltage would be controlled by external systems. You don't have any excitation circuit. So you remember that excitation circuit was used to control the voltage in synchronous machines. But since we do not have external, excitation systems in induction generators, we don't have a means to control the voltage. There are some advantages. These are simple machines, rugged, inexpensive, that can provide power. They are ideal for windmills, heat recovery systems, and small-scale distributed generations. We would always need some kind of reactive power compensation through means like capacitor banks in order to operate these machines. They do not have a good, voltage profile. As the load is increasing, you may easily go to voltage collapse. So you need to be aware of these conditions. Frequency variations, the output frequency will vary by the load, around 5%. Often acceptable to off-grid and emergency uses, but in modern applications, we really need to be careful with that. Because if all of your renewable generations are induction generators, they cannot have a good feature on the frequency of the system. They are used nowadays in small wind turbines, supplemental on-site generations. When connected to a grid, the grid would be providing the voltage and frequency regulation. So this means that these machines do not have a good voltage control, do not have a good frequency regulation control. And we always need to use capacitors to provide power factor correction.
So let me just go over the asynchronous generators really quick. So for asynchronous generators, the same way that we can utilize basically this machine as a motor, we can utilize it as a generator too. With one important consideration, considering the fact that when you have a motor, you always need some excitation current over here, okay? When you have a motor, you're feeding your circuit, you're providing that excitation current that is used for the machine to operate. But when you want to utilize this machine as a generator, the basically direction of power would be from the mechanical side. Here is the mechanical side towards the electric side, right? So here is when you're providing the machine. So you can see that there is no initial current inside here. There is no excitation existing in this generator, in this machine, to start its work as a generator. That's why to have an asynchronous generator, you have to have a means to provide that excitation. Because they don't have a separate field, no external excitation current is required. So that external excitation can be provided by an external capacitor or a power electronic converter to provide you with that required excitation current to enable this machine to work as a generator in the first place. That's because you're getting, basically, you operating the machine, you're getting the power from the mechanical side now, okay? And just keeping in mind that we said this machine works as a motor when the slip is something between 0 and 1, is smaller than 1. So when the slip is smaller than 1, this resistance becomes a positive number. Now, mathematically, if S becomes negative, what happens? If S becomes negative, these two are positive. S is negative, so the numerator is positive, but the denominator becomes negative. That's when you have an equivalent negative resistance. When you have a negative resistance, what does that mean? It means that you're generating power. Right? You're generating power. So this is the mathematical explanation of how this machine can become a generator. When you make the slip negative, what does that mean? When the slip becomes negative, it means that you're operating the machine above the synchronous speed. So that external mechanical source that you have, whether that's a wind turbine or whatever is rotational. The rotational speed that it provides for the machine should be above the synchronous speed. Whatever the synchronous speed of the machine is, it has to be above that. But add that to the other requirements, you have to have this current excitation, which can be provided using residual. So if you have a core that has kept some residual flux in it, that could be the initial source of that excitation current that is required to operate this machine as a generator. So a couple of things, like capacitors, external power electronic converters, or residual flux in some cases can. But these machines are being more and more used in wind applications. But keep in mind that voltage control would be an issue for this type of generator. That's because you have no excitation. So excitation is required for generator control. But they are, anyways, using power electronics. You can basically get rid of all of these issues and use these asynchronous machines as asynchronous generators, which is getting more and more popularity in wind energy conversion systems. This basically topic is on wind energy conversion systems. But the reason that I wanted you to basically learn more about this, because we're getting more and more integrated with renewable energy systems. So this is not a classical topic that you would see in the classical power system books. This is a newer topic. So I wanted you guys basically to become familiar with these new topics as well. So a wind energy conversion system is a system that is, as the name shows, is getting power from the wind and converts that into electric power for us. The abbreviation is WECS, Wind Energy Conversion System, is associated with all of the elements that are required to extract power and convert it into electric power. These include the wind turbine, gearbox, generator, transformer, converter, whatever is required to make that happen. All combined, we call them WECS, or Wind Energy Conversion System. In terms of the turbine, we have two types of wind turbines, HAWT, or horizontal axis wind turbine. So this is a horizontal axis wind turbine. As you can see, this is the axis, which is kind of parallel with the ground. So that's why we call it horizontal axis. And we have the vertical axis. So this is the vertical axis wind turbine. So horizontal turbines are used in high power applications. So when we're talking about wind farms, the big wind farms that generate a lot of power, most of the turbines in those wind farms are HAWT. Some of the advantages associated with these wind turbines are that they have higher efficiency because they are elevated above the ground. When you go in more elevations, there is more wind power existing than the surface. So they go high in the altitude. They can basically provide higher efficiency and have access to higher powers to long towers. Whereas in vertical axis, we have lower cost because we don't require that high tower. You can put it on the roof, for example. Lower cost. They also work independent of the direction of the wind. Whereas basically this horizontal axis wind turbines, they need to be faced with the direction of the wind, okay, to absorb the most power. And of course, the AWTs have the ability to work in lower elevations. So that's an advantage. They're lower cost, but lower power. They're mostly used for urban areas on your roof, for example. But HAWTs are used in rural areas where you have a wind farm. This was the first thing about the turbines. And then we have grid-connected versus off-grid wind turbines. So grid-connected applications are mostly associated with wind farms that provide a lot of power for us. Off-grid applications are mostly associated with rural areas when you have a basically farm far away from the urban area and you need power, renewable power, you can get the power, but it's mostly off-grid. You're not connected to the grid in that case. Also, we have fixed speed versus variable speed applications. So fixed speed is talking about wind turbines that can absorb the maximum power in a very limited, basically, wind speed region. So wind speed really needs to be narrowed to maximize, basically, the power that you're receiving from the grid. Just to give you an idea of why this is happening. So it turns out that with whatever wind speed we are at, like we are at 12 meters per second, for example, at 12 meters per second, which is a linear speed, the wind speed is also linear. The rotational speed of the machine, of the generator, should be matching with the linear wind speed. So for every linear wind speed, there is an optimum rotational speed for the turbine and the machine that needs to be basically there at that point so that you absorb the maximum power from the wind. If the linear wind speed changes, goes up, you have to change the rotational speed as well so that you absorb the maximum power. So that's why we call these variable speeds. They're always adjusting in order to maximize basically the power from the wind. So that's the major difference between the two. Of course, variable speed systems are more expensive. They're more modern. They use basically extra equipment like power electronic converters on the side so that it makes them behave like that, to be optimally changing the rotational speed of the wind turbine so that you can maximize the power from the wind. Okay. Now, I wanted to go through 4 different types of wind energy conversion systems, really quick, type 1 through type 4. So type 1 is associated with the squirrel cage induction generators. Remember when we were talking about induction generators, there was a squirrel cage, which had like shorted rotor bars, was very simple and sturdy. So these wind turbines work approximately in a very narrow range, or 1% above the synchronous speed. So this is a fixed speed, basically type of machine, which because the operational range is very narrow. They require reactive power compensation. They require soft starter. So if you connect them all of a sudden to the grid, they will give out basically a lot of inrush current to the grid. So therefore, you want to have a soft starter, which is a power electronic device that it works like a variable resistance that does not allow the inrush current to go into the grid when you in the startup. Okay, so these are the components that are required for this type of machine. These are fixed speed, lower efficiency. These are the first types of wind generators that came into market. They require reactive power compensation and soft start. Type 2 is using a wound rotor induction generator. So induction generator that is not shorted. It has basically connected to an external variable resistance converter that does allow the machine to work in a wider range of wind speeds, around 10%. So we go from 1% range to a 10% range. So we are able to maximize the power coming from the wind in a wider range. So that's an advantage. But of course, it makes it more expensive. They still require the reactive power compensation. They still require the soft starter. Type 3 is associated with DFIG, or doubly fed induction generators. Type 3 is a variable speed with DFIG, doubly fed induction generator. So doubly fed induction generator is a special type of induction generator that delivers power from both stator and rotor windings. So it's a basically fairly more complex type of technology compared to basically the fixed speed induction generators. 2 paths for power, stator and rotor. Rotor is connected to the grid through a reduced back-to-back converter. So this is the rotor winding connected to a back-to-back converter. It converts AC power to DC and then DC power again to AC, connects it to the transformer and to the grid, which gives us more flexibility, goes to 30% range, almost plus minus 30% range of the synchronous speed. This type and we have a direct path of power from the stator to the grid. So there are 2 paths for power. Again, if you really want to get more knowledge about these types of generators, you need to take other courses like Renewable 135. And at the graduate level, there is a course 257, which talks about wind energy conversion systems in general. So that's something for you to consider if you want to get more into these. So they can maximize the wind power in the plus minus 30% range. And they can work in both above the synchronous speed and below the synchronous speed. When we're talking about induction generators, we said that the squirrel cage needs to work above the synchronous speed. But in DFIG, doubly fed, you can go both above the synchronous speed and below the synchronous speed. So that's another basically difference between DFIG and SCIG. And finally, type 4. So the first 3 types were all using induction generators, type 2, 1, 2, and 3. But type 4 can use squirrel cage induction generator, permanent magnet synchronous generator, or wound rotor synchronous generators. Okay, the back-to-back converter So there is a full path between the generator and the grid. It is not partial, like the case that we had here in the DFIG. There is a partial route of power through the rotor. Here, you have the full path. So these are full capacity back-to-back converters that are kind of buffering the grid with respect to the machine. These are the most expensive one, but the most basically versatile one as well. Can harvest maximum power in a wide range of wind speeds.